So today we're going to talk about using the Niagara. Niagara is in production. We've all waited for a long time. We opened the gates yesterday. Some of you have been on, others have not. So we're going to talk about all of that. Now, we usually introduce these things in an intro to SciNet, where I tell you what SciNet is. I only have one slide over that because you guys know. But it's still in there, just if you wondered why. This is the SciNet Niagara user group meeting. We usually do this once a month or once every 2 months. We have pizza, so for the people on the broadcast, sorry, no pizza. For the people here, yay. For me, I haven't had my slice yet, so if I fall down in the middle, this is why. Using Niagara, what are we going to do with Niagara? So we're going to talk a little bit about SciNet. My name is Ramses van Zon, by the way. I'm an analyst here at SciNet. So I'm going to talk a little bit about what SciNet is, and then I'm going to jump right into how we can change from using the GPC, which is what most of you have used in the past, to Niagara. But also, if you're a new user, we'll skip after that to how you use this new supercomputer. And then I want to end with a few tips. This can be fairly loose, but because it's recorded and broadcast, will mostly be starting as a presentation. So what is SciNet? SciNet is the supercomputer center here at U of T, so that's where we're at. And we've been running massive parallel computers for almost a decade now. We're not the only game in the country. There's 5 similar consortia that do similar things. They host systems, and altogether we're part of the Compute Canada family. And so the way it works is, although we're all hosting a system, any researcher from anywhere in Canada can request access to them or can work on them depending on their needs. And not all the clusters are the same, and in particular Niagara is a little bit different from other clusters, which is why we're having this session, or part of why we have this session. There's also cloud systems for people that are interested in that under the Compute Canada umbrella. And then there's the 2 closely related systems, but different enough that we need to point at those differences. Cedar and Graham, so those are the general purpose machines. That's where you would run smaller jobs. But Niagara is meant as a machine where you run large jobs, so anything over 1,000 cores, say. This could still be but that's the size of a job, and we'll talk a little bit about what that means. So that's SciNet, and because most of our users don't really have a background in high-performance computing, HPC, or advanced research computing, ARC, we end up doing a lot of training as well. And so if you're interested in that, I just shameless plug here for our education website, and you can check that out on your own time. So that's us. SciNet is a fairly small group. We're all here at U of T, so that's convenient for those of you that are at U of T. We answer all emails and stuff like that too, so we supply the support as well. So let's talk about Niagara. This is our system. If you're a regular at these SciNet user group meetings, then you've seen this come by a few times as we got closer and closer. Niagara is our new largest supercomputer for academic research in Canada. Has about 60,000, or actually precisely 60,000 cores. They are Intel cores. They're 64-bit cores of the latest architecture, Skylake. And so the way that these are built is they're built out of nodes, and each node has 40 cores in it. So there's actually only 1,500 nodes, each of them with 40, and that comes up with the total. And they run at 2.4 gigahertz, so kind of in the range that anything runs at this time. And we've measured what the capacity is. There's a standard test that one can do, LINPACK or HPL, that gives you how many petaflops, so 10 to the 15 flops, floating points operations per second you can do. And this one is just over 3 actual performed. If you compute the theoretical of how much it could do 4.6. So it's normal not to get a peak, because that means that you're only computing and not getting anything from memory or anything communicates between the nodes, which means you have a trivial problem that you don't want to solve. So that's pretty nice. And that would have put us at the number 42 in the in the top 500 list. There's a top 500 of the fastest supercomputers in the world, or at least people that want their supercomputer to be known. So we'd be in the top 100, and I'm guessing when they make the new list in June, we'd still be in the top 100, I'm guessing. So that's nice. Canada's a little bit on the map there again in terms of speed. Other things you should know about these nodes, it really centers around the idea of nodes, is that each node has a certain amount of memory. It's depending on how you like to count, either in powers of 2 or powers of 10, it's 188 gigabytes or 202 gigabytes of RAM, which makes for about a bit over 4 gigabytes, or quite a bit more than 4 gigabytes per core. And that's nice, but that's very similar to most machines these days. We have Linux running on it. Any supercomputer runs on Linux. Our flavor is called CentOS 7. And we have a nice fast interconnect by InfiniBand, and the particular topology is called Dragonfly. And this sets it apart a little bit from other clusters. We have, and this is when you're doing parallel jobs. The different nodes have to talk to each other quite quickly, or communication becomes a bottleneck. And so we have one-to-one communication between every node and every other node, up to 432 nodes. So you have to multiply that by 40 to see how many cores it is. About 17,000 core jobs can run one-to-one. And then beyond that, it's effectively a two-to-one blocking. This means that theoretically, the message from one of the 432 nodes has to wait for a message for the other ones. But that only really counts when you're constantly communicating and not doing anything. So usually it's even better than that in practice. That's the network. The nodes have no GPUs. This is a bit unconventional for new supercomputers, perhaps. Why did we throw out the GPUs? It's very simple. We asked the users, what kind of big jobs would you want to run? And then we made a benchmark based on them, and we tried to see what is the best possible way to get the most science done. And it turns out the number of projects that want GPUs is too little to make it worth putting in GPUs, because others would have less nodes. We would have way less nodes if we went that way. So this is really science-driven or benchmark-driven. And it told us, for this system, this large system, what we need right now is a homogeneous system. That makes your job easier. That's true, because you don't have to offload anything to a GPU. And so that is convenient. But it wasn't for convenience. It was really just, what are people running? And this is what came out. Now, it's supposed to replace the general purpose cluster and the tightly coupled system that we had before. The tightly coupled system is already shut off. The GPC will be soon, in a few weeks. And we'll talk about how we migrate users from those systems to this. Any questions about the system layout? Most of you have seen this before. Okay, so if you are right now, so how do you get onto Niagara, and how do you get started with it? Many of you have been working on the general purpose cluster that we have, and that is almost at the end of its life. And so for those of you that have, or that were on the TCS, great news. You have accounts on Niagara. Your home and project content have been copied over to Niagara, and so it's all there waiting for you. Now, what we haven't done on purpose is to copy whatever was on your Scratch directory. Of course, we could have been even more brutal and say Scratch is temporary. We're just deleting everything from GPC, but not that bad. But the idea is this was working stuff, and some of it you guys want, and some you don't, and we don't know which is which. So it's up to you. There'll be a short period in which you will have access to the GPC Scratch as well as to Niagara, and you should clean up your Scratch, throw away what you don't need. If you have 200 terabytes in there, copying it will take some time. You might just not want to wait for that and just prune it until you have that 1 terabyte to transfer. So clean it up, and then you can transfer it. And we can help you with that, but we have some dedicated data mover nodes that are good spots for doing that, and that'll show in a little while. Okay. Yes, question? What's happening to Scratch? The current Scratch? Current Scratch will disappear. So those disk systems are out of warranty, and that's pretty much, they'll be there. So effectively, you don't have that storage anymore. Okay, so what if you weren't on the GBC? Now, most of you know about these national RAC allocation rounds, so resource allocation rounds, where every year your PI can submit a proposal for compute. If your PI, or if you're the PI, if you have received such a RAC for Niagara, and those RAC, and you would have received a message about that, if you have gotten an allocation in Niagara, again, your account will be ready for you. They have been created, and you can log in and get started. Now, that's what we've done, and that's what we could do. We haven't created an account for every possible person that we could find in Compute Canada. Why? Because it's a bit of a specialized machine, and because we had to get started. So we're still figuring out the best way to automate that, or to at least to facilitate that, how you can request to get access to Niagara. But for now, you can use the old route, which was to request the SciNet Consortium account on the CCDB side. It'll ask you to create a password for SciNet, which is a little silly at the moment. It's just that's legacy stuff. We'll phase it out, but that's an easy way. And we'll get an email saying, hey, somebody requested access, and we know what it means. You want Niagara, and we'll make that happen. Okay. You can also write to support@scinet.utoronto.ca. Again, we'll pick it up. This new account creation is still being fleshed out. Okay. Okay, so suppose you have your account. Great, now you want to get started. You want to use that supercomputer and do your fantastic science. Now, as most of you will know if you've been on these systems, you will log in with SSH. That's how all SciNet, all Compute Canada systems work. That's how you go in. So you'll need either you need a terminal window. So if you're in a Linux machine or a Mac, that's pretty easy. And if you're on Windows, you can do something like MobiXterm or PuTTY, or there's a variety of possibilities. But you log into to the Niagara login nodes. So there's different kind of nodes within Niagara. These are the login nodes that you go into. And there's two routes, just because we first got niagara.scinet.utoronto.ca up. That route works. An alias for that is niagara.computecanada.ca. But what's important to realize here is that your username here is the username for Compute Canada, so for the Compute Canada database. So this is not, for a lot of you, that's the same username as you had in SciNet, and for some it is not. So just figure out which one is which, and use your Compute Canada account. The idea is that whatever you use for the other clusters to log in, like Graham and Cedar, you can use here too, and it'll be easy. Oh yeah, and the password also is that one of your Compute Canada one. So if you had your SciNet password, that's great, but that's no good in getting into Niagara. This will eventually make it easier to get new accounts too. So this whole creation of accounts will be easier, but that, as I said, is in development. If you want to do any graphics, don't forget the -y. It will allow you to open Windows from the terminal, provided you have an X server. Those are details I don't want to really go into, but that's what the -y means there. So those are login nodes, and the login nodes are a little bit like the old development nodes in the GPC. That's where you're supposed to edit your files or compile your application, prepare your job submission script, and submit them. That's what you do on the login nodes. They have the same architecture as the actual Niagara compute nodes. The memory configuration is a little bit different, and the number of cores is different, but they're shared. So on those login nodes, once everybody learns about Niagara, you'll have like 100 people on each of the login nodes. There's, I think, 6 in all, but still. So you can't run anything on that, right? Even if it has 32 processors, 100 users are going to overwhelm that. This is not where you compute. This is where you test a little bit, where you compile, and then you want to send it to the compute nodes. So you do that through a batch job. We'll talk about batch jobs later. But before you're there, you want your stuff. Where's your stuff? As for all of the Compute Canada machines and all of the previous SciNet machines, You'll have a home and a scratch. Home is where the heart is. Home is where your files live. Home is where you put what is dear to you because it gets backed up. Okay, but it's not terribly big. It's nice and big. We've got 100 gigabytes for each user there. That's nice. It will be backed up. Backed up, by the way, means we have a latest snapshot. Don't go ask us for the version of your file 6 months earlier. We don't have that. It's a safeguard. It's not an archive. Yes?
You said 100 gigabytes?
100. 100, yeah. Gigabytes, yes. So nice, but no, yeah, it's nice. Okay. Now, for anything bigger than that, or for stuff that you need during your run, we have an area called Scratch. And so these live in kind of longish names. So for me, the group name is part of your path and the first letter of the group. So for me, I am in home, S, Signet, Arzon, which happens to be my username, and Scratch is under Scratch. Because it's a little annoying to work with these long paths, and because we might at some point move them, hopefully not, but we might, we have environment variables. Home is actually already defined by the Linux operating system, so that's easy enough. And Scratch is defined as well. So if you want to work in Scratch, you should just cd $scratch, and that leads you right there to your directory. Now, if you have an allocation, a rack allocation, you have an additional space. It's called project. The allocations are for a project. It's kind of an apt name. And they live in a similar directory structure, project, group letter, group name, username, but you should really use $project. If you don't have an allocation, by default, you don't have one. Unfortunately, we don't have as much space as some of the general purpose machines. So if you have a good use case, you can email us, but in principle, this is for allocated usage. This is why the home directory is a little bit bigger to sort of make up for that. Make sure to use these environment variables, already said that. Just makes it safer. Also means that if you have a job script and your colleague in the same lab wants to run a job, you just give it the job script and it still works because it just has $scratch. It doesn't say it's their path. So that's a good practice. How much can I put in there? I hear you ask in your minds. So I already mentioned home has a 100 gigabytes limit. It doesn't expire, and it is backed up, and you can see it on the login notes, but we've done something sneaky. You can't write to home from the compute nodes. We do it kind of as a safeguard. You can't accidentally overwrite your files by running your job from the wrong directory. It also means our backup can be done more frequently so that there's less turnover. So it's all kind of good stuff. But then why do you write your stuff? You write your stuff to Scratch. So if you're actually running in a compute node, you will have to write to Scratch. Now Scratch has a large quota, 25 terabytes. That is a joke. That is about 10 times oversubscribed if everybody starts using that, and that is now, before we have even more users. This is a safeguard again. Some people will need it, others will not. So we just put it as a safeguard so nobody fills up the whole disk. That's what the 25 terabytes means. It doesn't mean you have 25 terabytes of storage. It means you have 25 terabytes to play with and then throw it away. Okay. Because of that, there is an expiration time to files on that system. It's 2 months. Again, this is kind of done nicely. The idea is if you have data on Scratch that you are actively using, we don't want to delete it. So it's not based on when you put the data there, but when you last accessed it. So if you access the data today, but it was created 4 months ago, it doesn't get purged, doesn't expire. We keep it there because we know you're using it. So it's based on last access time. It's not backed up. It's really for temporary data, but you can see it on both the login nodes and the compute nodes. The project is nice for people that really need storage. So if you need storage, if you know that you don't have an allocation next year, next fall, ask for it. Say, we need some storage there. We need to keep some of this stuff. And then there won't be any expiration. It will be backed up, and you can do whatever you want on login or on compute. Okay. So that's for those people that have project. Then there's 2 things that we have that not every other site have. We have a thing called archive that actually doesn't exist anywhere but in a special system called HPSS. Some of you have worked with this before. It's a tape-backed archive facility. And so that is meant for stuff that doesn't have to live on project. Say you have some data that you won't need for 6 months. Having that take up space in project or in Scratch seems wasteful, and it is. So you can move it to archive. And that, again, usually is by group allocation, but there too, we can be a little bit more helpful if you need stuff saved. So that's special, but that's sort of for other sites call it nearline or archive. We have that too, and they're working on that in the other sites as well. And then we have a fifth version, which isn't quite operational yet, but it will be. It's called burst buffer. So Scratch and Project are nice parallel file systems that work really well for large files that are written to or read from many nodes at the same time. Doesn't work very well for small files or small I/O or rapid I/O. And so there's a need sometimes to do that. And for that, we have an extra tier called burst buffer that is faster in almost all respects, but it's a lot smaller. So most likely, we'll want to configure that in a way that your job requests a certain size of burst buffer, and maybe what your job wants to do is run and then checkpoint its state to make sure that if it crashes in the middle, it doesn't, or to restart. But it doesn't want to waste time to write to disk. Right? If you're waiting 12 hours for your 24 run to checkpoint, it doesn't make much sense. Burst buffer is much faster than that. So there'll be more information on how we do that as we configure this, but it'll be a nice tier to have, and it'll be very useful for a lot of workflows. So those are storage options. Most of you are going to work compiling in home and then working in Scratch, or if you have a project, working in project. That's going to be the workflow. Okay. Block sizes matter a little bit too. So home has been optimized for small size files. Makes sense. If your code is there, code is lots of little files. If you're on Scratch, the block size is bigger, and it's really meant for larger files. Don't have little files. But I have more to say on that later. Here? Okay, there's no questions in the room. Okay, so that's where you can be. How do I get my data there? I already had data. Where is it? I already told you that if you had data on GPC's home and project, that's already transferred over, so that's easy. If you're moving data from elsewhere, there's sort of a rule of thumb that you can copy it through the login node, so an scopy or an rsync will work. But if it's more than, say, 10 gigabytes, that's going to be troublesome for a couple of reasons. First, the login nodes will cut you off because there's a limit on how long you can be running on them. So that's not good. And it's also not the fastest connection to the outside. So we have data mover nodes that have a larger pipe to the outside, shall we say. Data mover 1 and now also Nia data mover 2. But it works kind of funnily. We don't want everybody to just be hammering that. So you have to come from the inside, go to the login node, and then SSH to one of the data mover nodes, and then start pulling things rather than you from your computer pushing things to the data mover. But then it will work. That does mean your machine has to be accessible. So sometimes in a lab, we have to do some things for that. But, okay. I won't talk too much about Globus, but Globus is a nice way to do this in a web interface if you do this kind of stuff often. It's not set up yet for Niagara, so that's why I don't want to linger too much, but it will be available in due course too. And then finally, I talked a bit about HPSS, but it's its own system. To get data in and out of HPSS is basically a batch job. And it is because actually the type library is there, the tapes are stored, and whenever you submit such a job, when it's your time, the robot goes and picks your tape and puts it in the drive. So it's a slow process in principle. Like it's not so it's by nature a batch system that goes that way. Okay, so that's storage and how to get things in and out. How about software? So once you're logged in, what's there? And so much as on all of the other clusters, there isn't much by default. And the reason is there's a large user base. There's very many different kinds of packages and packages that might have conflicts, different versions of the same software package that people would want to use. which means there's no way to just install it and have it be readily available. What happens instead is that you take, you have to activate these packages. They're installed. You have to activate it by a module command. And so it is installed, this software, and I'll show you how to get the list of installed software. But you have to activate it or make it part of your environment with a module command. And that way you can pick out exactly the version that you might need. All it says it does is set some variables. It's not an actual installation, so that's why it's really quick. And we can have multiple conflicting versions. Now, if you want to know what's available, you have to use the command module spider. We're using a flavor of the module system called lmod. That's the same one that they used on Graham and Cedar. And spider is its command to show you what's available. So if you are logged in to Niagara, so you did ssh niagara.computercanada.ca or signet.utrons.ca, and you have your prompt and say you landed on login 07, and you typed in module spider, you would see something like this. It's a long list. I cut it off. It's alphabetical, and then apparently capitalization matters in that order. In any case, there's a bunch of these modules. We'll talk a little bit about them. So once you've seen that list and you spotted something you like, you can load it, just saying module load and then that module name. If you've loaded a whole bunch of stuff, you just want to start over again, you can do module purge to remove all the loaded modules. Module spider we just talked about, but there's a number of extra uses of having spider find things for you. There's module avail, which is funny, and I'll talk about the combination in a second, and module list to see what you've loaded. So there's a snag in using Niagara versus when you're coming from Cedar and Graham, is that we really have two software stacks. So the general purpose clusters at Niagara, at Cedar and Graham are on purpose are very similar. And so they have an identical software stack. Niagara is aimed for large parallel jobs and will at least initially have somewhat of a different software stack. So that makes that there are actually two software stacks. One is sort of Niagara native, and it's the one that you get by default. So if you don't do anything, you're logged in, you don't have any modules loaded except that module that gives you access to the Niagara stack. If for any reason you lose that stack, module load nia and we'll get it back. The second stack is the general purpose cluster stack, so the Compute Canada stack. And one of the reasons we have two is that for now, that stack doesn't support all of the newer CPU architecture. And so it will at one point. It isn't now. If you want to use that stack, you just do module load ccnv, and it replaces the Niagara module set with the CC module set. After you've loaded this, things will look the same as they are in Cedar and Graham. So if you're coming from there, that's great. But if you want things that are optimized for Niagara, you might want to play around with the first one. And because we'd like people to run as efficiently as possible, for now, this is our default. Okay. Yeah. Now, one thing that we do, and we feel this strongly, is that when you log in, you shouldn't have any modules loaded. Why? Because at some point, you're going to change your workflow. You've worked on a machine for a year or two. You have a new project. You need a newer compiler. But all these other things are loaded by default already and are now conflicting with your new jobs. So the best thing to do is not to load any modules by default. But it's not how it's set up in Cedar and Graham. If you log in there, you get some default compiler, a default MPI, and some other utilities. And to get rid of them, you have to module purge yourself. So it's the opposite way. So if you want those default modules loaded that you had in the other systems, after you load ccnv, you load their standard environment, stdenv. So both of them would be necessary to get the identical experience from the other systems. So this is possible. They're sticky, but you can look up what that means. So that's how the modules are laid out. Let's look at a few extra things we can do. So I already said I don't like default modules. Although we don't put them in there, people like to put them in their bash or C. And again, that seems like a good idea. If you know, the .bashrc is a file that's loaded when you log in and when you run scripts. And so if you always use the same modules, you can save yourself time by putting module load commands in there. But eventually, you're going to change which modules you want. And now funny things can happen in the end. So best to be explicit. This is the modules I need. If I want to run a job in my job script, put your module load commands there, and you're sort of safe. And document it on what is loaded. So do things by hand. Another thing that I would advise to try and get used to is that, well, you can just load modules by their short name. So the modules all have a name and then a version number. For future reproducibility, it's probably best to include the version number. So right now, the Intel compiler on Niagara nicely resolves to Intel 2018.2, which is the newest Intel compiler suite. That's great. On the GPC, we did this too, but we did it when we installed it. And so for them, for the GPC, you got the 2012 version of the Intel compiler for the entire lifetime of the machine. So that's not ideal. The best is to be explicit and say, I want the newest version, or I want this version, and also for reproducibility. There are some handy abbreviations that after a while you can't live without. If you want to do a module list, you can just type ML. If you want to load a module, you just can do module and then the module name, so ML name. And if you want to do anything else, you just do ML again. So after a while, you'll never type module again until you get onto a system that doesn't have the ML command, and your fingers are all crossed. Okay, so that's the basics of the modules, with one additional thing. Not all modules are independent. Some modules require other modules. We had that on the GPC and the TCS as well. You wanted to load, say, an Intel compiler, an MPI compiler, you had to load an actual compiler as well. The same is true here, but it's set up a little bit differently using module spider. So let's look at an example here. So module spider is an odd name for what's essentially a search and advice facility for modules. So if I want to know if there's OpenMPI on the system, I can try a module load OpenMPI, but then lmod, which I said is our flavor of the module system, detects an error. And it says, well, I have OpenMPI, but I can't load it. I can't load it as requested because of something. So why don't you try module spider OpenMPI, and I'll tell you what to do. So you try module spider OpenMPI, and it goes, oh, OpenMPI, I've got a couple of versions of those. Now, if you want to know how to really load it, why don't you try this command? Looks like it's sending you around in circles, but this command actually gives you something useful, because if you do module spider OpenMPI with the version number, it says, yep, I've got it, and this is what you should do to load it. So if you want to load this module, you should first load these guys. By the way, so if there's only one version of a certain package, you skip the middle step. On the GPC, we had module avail, we had module find, and module advice that you guys might have worked with. This essentially replaces that with one command in 3 different ways. So once I have gotten my advice, I go, OK, so I have to do module load NIA env 2018A, Intel 2018.2, done. And I can now load my module. And indeed, I get no more error messages. I'm just doing NIA env here because you will probably just cut and paste this. NIA env will be mostly loaded by default. So really, you just module load Intel, module load OpenMPI. And then if you list it, you will find those are there. OK, so the resolution is very similar, but it's all the spider command. So that's the default, that's the installed software stack. Commercial software. People will try and run commercial software, will ask, do you have a MATLAB license? Can I run ANSYS on your system? Things like that. And the answer there is perhaps, but we're not paying for it. And that's not because we're cheap, it's because we're poor. We don't have enough money to buy everybody's favorite license. There's too many different people here with different packages. We can't possibly do that. It's not feasible. So we turn it around. You can, sure you can, but you have to come with your own license. We also have, in case you don't have a license, some alternatives. So if you're running MATLAB, if your script is fairly simple, you might check out Octave. R and Python are very useful scripting languages, can do a lot of things that you might want to do otherwise. Otherwise, there's ways to make things work, but you just contact us and we'll see. If you have a license and it allows you to run on a cluster, we can make it work. Okay. It's just not automatic. Yes.
How do you transfer in GPC?
So for the question is, if you had licenses on the GPC, how do you transfer? There's two kinds. There's those that were just contacting license servers in their own department, and that essentially will go the same way. So there's an SSH tunnel you can set up. For a few cases, I think we've run a license server locally, and just contact us and we'll do something similar. Yeah. It's not entirely automatic, but just contact us and we'll set it up. So just a quick example of how this would work if you're compiling code. I have just my standard Niagara module loaded. I load an Intel compiler, and in this case, I want the GSL library, say, because it's needed. And then I can compile some C code with the regular flags. If you're compiling flags, if you're doing this for the first time, make sure you turn on some sort of optimization, -03. Try and do -x host as well. This is for the Intel compiler specifically, which makes the code run as best as possible on this architecture rather than compiling for any old x86 or architecture. And you can link, and then you can run your stuff. So that's it. Most of you would have a makefile or a CMake file, or maybe just some other build system. It's fine. The module load should do everything for you before that. Oh, going too fast. Okay, so I'm running this little command there. That's wrong. But it's also right. It's wrong because you shouldn't be running computations on the login node. But it's right because you should be doing something called testing. You've compiled it. You have a binary. You don't want to ask for a 1,000-core job and launch it off and have it find those jobs and then realize that it crashes right away. It's hard, and it's not very useful. So you want to test on a small scale whether your stuff is working. So please do that. You can run small tests on the login node. So no real computation, but anything that takes a couple of minutes and say 1 or 2 gigabytes of memory, or maybe even a little bit more, that's fine. Just make sure that things work. We have the DDT debugger available as well as a module. So if you want to do parallel debugging, this is a nice one. It's now under the ARM flag, but it's in the DDT module. Now, if you find that even your little test is not giving you anything, or you have found that it worked, small scale, you ran a real test, a real computation, still crashed, you need to debug on larger scale, you can use debug jobs. So we have a little debug queue or debug partition that you can use for that. And so all you have to do is type in salloc, which is a slurm command. We'll talk about slurm a little bit more, to get an interactive job. So, and then you'd have to say -p debug and the number of nodes you want and for how long. So you have a few nodes set aside that you can do this for. It's for a short time, so there's high turnover. There's a high likelihood that you can actually get one of these nodes. But then you get a whole node. Now, if you remember at the beginning, I said the node has 40 cores. Those cores are now yours for the duration of this, if n is 1. And you can launch up DDT. You can do your parallel debugging with those 40 nodes up to an hour. You better find your solution before that, or you'll have to start afresh. So that's there for sort of larger scale testing, that things that didn't surface on small scales that work on the login nodes. So that's great. We have that. We have a little debug queue. It's not very long, so you can't really do any production on it. But it's there for exactly this purpose. So suppose you've tested. We have compiled. Now I want to run. What? Sorry, yeah. Yeah, 4 nodes. So it gives you 160 jobs. Now our limit on the DDT license for parallel debugging is actually 128 processes. So that's kind of where the size was. There was another question there. No, or at least not yet. I might just put it in. But we had a nice, the question is, does the debug job command work, we had that command on the GPC, and it's convenient because you type debug job and you basically does this command for you. We might put in a little script that does that, but this will work now. Okay. By the way, the slides on this are on the website, as will be the recording. So if you're taking notes, that's fine, but the slides will be there. Okay, so submitting jobs. I already mentioned this name, but Slurm is the name of our job scheduler. So we have our 1,500 nodes, and some machinery has to make sure that these are fairly allocated. And Slurm is the one that is doing this. And you do it by submitting jobs. So you'll create a job script that tells the scheduler what resources you want and what you want to do with them. So suppose that is encoded in this file javascript.sh. You give that to the command sbatch, and it puts it in the queue. When it's put in the queue, eventually it will run on a compute node. Queues are always busy. We've opened yesterday, and I think we're already 100% utilized. That's why you need this scheduler, right? So there's limits in place so that nobody takes those 1,500 nodes and uses them for the rest of the year. And so these are the limits. 24 hours is the maximum wall time you can have. It was 48 in the GPC and TCS. I know there's longer queues on the GPs, on the general purpose clusters. We stick to 24. We kind of have to. We wanted to make it smaller, but that seems a little unrealistic. Why? Because we want to run big jobs. So sometimes people do need 400, 500 nodes. And if they need that, and there are jobs in there of 2 or 3 days, that means that these, first of all, have to wait a long time, but also some of these nodes aren't doing anything for days, just waiting to make room for this large job. So having smaller jobs means faster turnover, which in the end helps everybody. So that's one. The scheduling is by node, and this is also different from the other clusters, which means that you always get a multiple of 40 cores to work with, and an exact multiple of the 202 gigabytes per node. It's kind of easier to think about it, but it is your responsibility to use all those 40 cores on the node because nobody else has them. So you must write to scratch because home must read only. And another thing to notice, this isn't often an issue, but the compute nodes don't have internet access. So if you have any data that you need to download, do it first on the login nodes and then submit your jobs. The idea is these are long-running jobs. These aren't scraping from the internet. And, this is computation rather than. No, so the debug jobs are just like compute jobs. They're really meant to try out stuff as it would work on the compute node. So also the debug jobs do not have that, which means that if you're running the debug job because, say, your compilation takes too long, you're in trouble because you can't write to home and you can't download from the internet. So we're working on proper limits to make sure that on the login nodes you can do everything you need to do. And if you hit a limit, just send us an email and we'll work around it. The scheduler is pretty fixed. Like we're not going to go over 24 hours anytime. We're not going to go away from by node scheduling. But limits on logins or getting things done otherwise, we will totally help with. Any other questions? All right. So as I said, we're scheduling by node. So I wanted to sort of briefly dwell on that. It has a lot of advantages. It also should be possible. This is a large parallel machine. It's for large jobs. If you don't have use for 30 nodes, then you don't need to use Niagara. You can use any of the other clusters. And if it's really small, maybe even your own cluster. So it's possible. But it also means a couple of nice things. The nodes that you run on are only yours. The only way that other users can do anything bad to your job is through the shared parallel file system. And we will hit them over the head for that anyway. So we've got us on our side. So it's your job. It's also more secure. Whatever you do there, other users can't see it. They're completely non-shared, completely exclusive. They are yours for the duration of the job. So if you have something running on those compute nodes, you can SSH into them. If you don't have anything running on them, you cannot. Okay, so if something's off, and the standard tools don't really tell you what's going on. SSH, type top, type PS, see what's going on with your memory, attach a debugger if you want. You can do whatever you want. They are your nodes for the duration of the job, so that's nice. But you'll always get a multiple of nodes. So think of nodes. Don't think of other resources when you're working on Niagara. It also means that memory requests are of no use. They're all the same. They all have 202 gigabytes. If I ask for, there's no point for me asking for a terabyte. There's no terabyte nodes in there. You ask for nodes and you get 200 gigabytes times the number of nodes distributed, right? It's not so the 200 are shared memory. It's kind of simple in a sense. Once you made the transition of thinking of I'm getting n nodes, the rest just follows. It is your responsibility to use all 40 cores on the nodes. You don't want to be wasteful. If you're running a serial job on a node and you're just using one core, that means that we're still paying electricity for 39 other nodes, and 39 other jobs aren't doing anything. So we can help you get your workflow going if you have non-parallelized jobs, but very many of them. And just either contact us or just look up on the wiki how these things should be done. This is possible, right? But it is your responsibility to do so. So we don't have a scheduler to do that for you. If you don't, we are going to monitor what you do. And we're going to see, not in detail, but we're going to see what your CPU utilization is. And we're going, this guy is using 1 out of 40 cores. We best contact him and tell him that he can get more science done if he did things differently. So in the end of the day, being inefficient hurts other people, but also yourself. And so we're very helpful in this respect. We'll really help you with this. Yes, we'll be very helpful because you don't want to waste time waiting for a job that is inefficient, right? You don't want that. Okay. It's all about the science. Yeah, sure.
Can you say again, like you can log in and see how it's going, but like see what are you going to see?
Well, you can see the same thing as if you were running it on your own computer.
But it's running.
Yes, you can see if it's running. You can see how much memory it takes. You can see if you know the tools. You can see if it's doing this kind of. No. You can. There's tools. They're just Linux tools. Like top tells you what processes are running. Free tells you how much memory is free. So and especially while you're running, there'll be eventually some sort of monitoring that goes on that automates some of that. Like every 20 minutes, there'll be a snapshot, and then you can view that. But this is sort of live right there, and not all of those tools are in place yet. So this is your best guess right now. Yeah, sometimes you just want to know if is it really running. Like it's not giving any output. Well, but if it's still at 4,000% CPU, it's apparently doing something. So you go, okay, I guess it's doing it. So yeah, being able to go into the node can be very useful if whatever other tools are there aren't giving you enough information. But it's just as if you're logging into a Linux box, and whatever tools you would have there, you have here. Yeah. Mm-hmm. Yeah, in principle, yes. Now, of course, the next step is probably going to try and do it in a debug job, because then, and there we don't care. Like you don't on purpose. Like if you're using one core on a debug node, yeah, that's fine because you're trying things out. That's what it's for. So that's where. So be wasteful on the debug queue and be efficient on the compute. And yeah, does that make sense? Yeah.
How many threads do I have follow jobs?
Basically you're gonna test small scale and extrapolate and first time around hope for the best. That's the thing with science. You don't. I have the same problem when people ask. I don't know what to ask for my rack allocation because I don't know. Yes, you don't know, so you just try, you do your best guess, and it will change, and you'll find that you were really right or really wrong. It's the nature of our enterprise. Okay, so finally, well, not finally. So hyperthreading is something I should talk about just because it will confuse you. I said there are 40 cores per node, but the operating system will tell you there's 80, and certain Slurm commands will tell you there are 80. That is odd. What is going on? This is a technology called hyperthreading, and it's something that leverages essentially more of the physical hardware in the chip by pretending that it has twice as many cores than it has. So some things can be done in parallel on a chip, but it doesn't really work very well unless you pretend that they're different chips. Why that works is not really our point, but that it works is a point. Using hyperthreading typically gives some speed up. It's not twice as big by pretending to be twice as many cores, but it's like an extra free 5% or 10% of performance. Not for everything, but I haven't seen slowdowns since the early days of hyperthreading, so we just enable it. Occasionally, it makes absolutely no difference. Fine. But that's why you see 80 logical cores or logical CPUs, whereas there are really 40. In the end of the day, it's the 40 that we bill you on. Like if you had 40 core years, well, that's a little bit little. So 40 core years, then you'd have one node sort of for yourself for the year, not half one. So it's a real cores that we count on. And so an easy way to just get used to this or to use it is just first ignore it. Say, no, I want the number of nodes, and on those nodes are 40 cores, and I'm ignore the fact that there's 80, and I'm just going to try my things out. Once they are working well, I'm going to see, oh, but what if I bump it up? Does it get any faster? And then I'm using it. So basically, I want you to ignore hyperthreading until you have your production runs ready, and then you go, okay, just let's see what we get for free in addition, and that's where it goes. If you just run with 40 and you don't do this last, let's see what it is, we're still happy with you. We're not going to ding you for not using hyperthreading. I'm just saying this is there. It's yours for the taking. It's on a single node. So this is where making things by node is easy. You get a node. The node has 40 cores and 80 logical cores. You don't have to know. You don't ask for cores. You ask for nodes. And so you get them. Yeah, just try it out. Okay, took a while to get here, but this is what a submission script should look like. This is an example for when you're running purely threaded code, so OpenMP in this case. The syntax of Slurm is a bit different from that of Moab and Torque that we had before. Instead of pound PBS, you will see pound sbatch, and the names of the options are a little different. That's why I wrote them out in full. There are short versions too. You can do -N instead of -- nodes, but for slides, I find the long version more informative. So what this does, is much as any other scheduler, is it takes all these pound sbatch lines and feeds them to the scheduler as requests for resources. This requests one node on which I'm going to run 40 tasks for 1 hour. And that's basically it. The rest is just tweaks. Here's a job name I want the job to have, and I can tell it where to put output. And the output can have some identifiers. This is, for instance, a job ID. So if I run it again, it doesn't go in the same file. Oh, it is the output that the script would produce on screen. If you just ran it, that's it. Yeah, standard out. Yeah. So, and by default, output goes both standard out and standard error. So error and output. If you want errors separately, you can do -- error equals, and then it separates them out. So by default, it just collapsed them together, which it was the opposite for PBS, where the default was to have them separate unless you collapse them. But you can do the same thing. So this goes to the scheduler. It goes, okay, you want a node. You're going to run 40 tasks. Put it in the queue, and I'll see when I have time for you. Once it gets a node, it finds that you are entitled to a node, it puts your script there again and runs it. And so it runs this script pretty much verbatim. So what it does then, once it has that node and has given it to you, is, in this case, change directory. Slurm submit directory is the directory from which you submit it. So that's nice. It makes your script a bit more portable if you do that. I'm loading the modules again. You have to do that, otherwise they're not loaded by default. And in this case, because it's an OpenMP application, you want to set the number of threads. Again, there's a slurm variable that is basically whatever you set in the CPU per task, but now your script can know it as that variable that you want to set your threads to. And then you run your command. If this is your script, you put it in a file called openmp_job.sh, and you give it to sbatch. Okay. So you write a script that does what it's supposed to do. You put in a few special things that come from Slurm, and you put a header in here. A few things as we're doing it here anyway. CPUs per task is essentially how you set the number of threads. Okay. So, and it talks about CPUs, but it's really just threads. That's what it means here. Slurm has some funny ways of calling things. Yeah, sure.
What's the difference?
There is a slight difference. For this, functionally, there is none. If you do srun, then there's a command called saccount, S-A-C-C-T, that will actually give you information for each srun. So if you wanted to know memory usage per case or something, then srun, I think, gives you that, whereas not srun would just bump it together with the whole thing. So there's slight differences, but functionally, for this stuff, they're the same. MPI is will be running a lot on Niagara, obviously. The big difference here is the number of nodes will be bigger, but you have to ask for a certain number of tasks. And by task, Slurm means MPI processes. Okay, so I want to run pure MPI, so 40 tasks per node. I'm not doing hyperthreading here. So I'm just do the multiplication here, ask for an hour. I'm not asking for cores. I'm not asking for memory. That's all automatic. I got my 8 nodes. But I do have to ask, funnily, about the number of tasks. But it's really so that when I call my MPI run here, it knows how many processes to launch. If I forget this, I just say 8 tasks, then it's going to run on 1. Or I specify it by hand. So it's just, this is a little bit more neater. And especially when you're doing hybrids, MPI and OpenMP, you'll have to do n task and number of CPUs per task at the same time. But if it's pure, it's not that hard. I'm obviously loading some different modules, but that's the same. Here, instead of MPI run, you can also do srun. They should functionally be the same. I've had slightly better scaling luck with MPI run as srun, but you have to remember, when you're using Niagara, these are early days. Some parameters might not be tuned optimally yet. Let us know if you have any problems. Just let us know. This thing crashed. I don't think it's my code. We might tell you, yes, it is your code, or we might tell you, oh, thank you for telling us, because we need to tweak something. Okay, help us out in the early days. So right now, I would advise MPI run, just because I know it works. It works well. I've tested this. In principle, srun should work just as well. And the difference is going to be, again, the same. With srun, it will actually tell you after the fact how much memory this example took. Whereas with MPI run, I think it collapses them all together. So the counting is a little bit different. You don't really care, because at the end of the day, what are you built for? 8 nodes, 40 cores for whatever wall time there is. If your stuff finishes before the 1 hour that I asked for here, it gets killed. Not killed, it's done. It gets taken out of the queue. That node becomes somebody else. So now you might be saying, well, then I'll just always ask for 24 hours. That's easy. You don't have to think. And that's true. You could do that. But if it's a smaller job, the scheduler might find a little hole in the schedule where it's waiting for a bigger job to go. So it actually pays off to have a reasonably accurate estimate for your time when you're submitting your job, because it'll run quicker, not faster, but sooner. Okay. Yeah, no, we will need them. We have less nodes than we had before. They're a lot fatter, but we have less nodes, which means backfill becomes more important. Okay, so then a few commands. There's a lot more Slurm commands to monitor your jobs, but SQ is the main one to look at what is queued. If you add -u and your username, you just get your jobs. If you do SQ, it becomes a really long list of everybody. It's not very useful, but you get an idea of how busy it is. You can look for a specific job, and then it gives you all kinds of information. If you know how to tweak all of the parameters, you can even get an estimate for when your job might run. This is early days. I have no idea how accurate that estimate is or if it even gives you one, but try it out and let us know. If you want to cancel your job before it's done, you can do cancel-i with your job ID, or you can cancel all of your jobs. Be careful with this one. But if you are sure that all of your jobs should go, you can do it all at once. And if you want to know some information on what nodes are available or what's running right now, sinfo will tell you that. Now, sinfo will tell you things about the compute, about the debug, and about a few other queues that we have. You just want to do -p compute and just see that one, because that'll tell you exactly what's up. Yeah.
Where to run any serial jobs?
There is, but not supported by the queue. So you would ask for, say, a node for a certain time, and then in that node, to run serial jobs, you would use something like GNU Parallel or similar task where you make sure that there are 40 processes running at the same time. In the simplest case, you just run them in the background in your script. So you say command ampersand, command ampersand, command ampersand. You want to do a bit more careful logic, because now you're typing that in 40 times. This worked well on the GPC because you only copied 8 commands. There were 8 nodes, 8 cores on the node. This is good. But yes, you can, but you have to do the work yourself or use a tool that does it for you. The job arrays, yes. I think they're supported. I haven't played with them, but nonetheless, you can still not do serial jobs with those. So you can have an array of jobs, but each job would have at least 40 cores still. So this can be very useful, I guess, if you have many of them. Sure, yeah. Okay, we're almost at the end. Congratulations. Okay, some final tips, especially if you're new to a cluster. If you've worked on the GPC, you've heard this many, many times. And if you've worked on any of other clusters in Compute Canada, you also have heard this, hopefully. When you're dealing with parallel file systems, like the ones on Home, Scratch, and Project, these are very nice systems. They're mounted everywhere. You don't have to copy files from one node to the other to get things running. They're already there, and they can write in parallel in a backend that has many drives running at the same time. Our particular file system is called GBFS. Other systems have Lustre. Doesn't matter. When you have a parallel file system, these are meant for that kind of large-scale stuff. Fast reads and writes for large data sets. That's what it's for. But because it's designed that way, it's actually not very good for small files or small I/O or little reads or writes all over the place. That leads to poor performance. It's not that it won't do it. It'll just be slow. And since it's shared, if enough people are doing this kind of, let's call it bad I/O, everybody will see that the system becomes sluggish. The file system becomes sluggish. You do an LS, you're waiting a little while, and there it is. Right? You don't ideally want that. It's how one way you can tell somebody is doing bad I/O. So a few things you want to do to avoid that is not read lots of little files or lots of little amounts of files of data to disk. Don't have a file and jump back and forth. Think of it as the bigger the chunk can be, the better it is. It should be red and bold. Yes, it probably should be. They also waste space because of the finite block size. Like a 1 kilobyte file takes 16 megabytes. It's kind of wasteful. So it's bad on all kinds of stuff. It's also bad on your system, your own laptop or your own workstation. You just don't know it. You make the kind of modifications that we would advocate here, and you suddenly find your stuff runs faster on your machine as well. Yay. Right? Write in binary. If you have numerical data, don't write it in ASCII. It's faster. It takes less space to do it in binary. So do that. Now, finally, if you have a workflow where you can't help it, you just have kind of bad I/O, but you know it, we might still be able to help you out. This burst buffer storage tier that I was talking about, that we haven't completely configured because we don't quite know what you guys want to do with it yet, will be much better at doing that kind of I/O. And so it could be a safe, sort of a safe haven for that. We're thinking of checkpointing, as I said. So your job is running, the 24 hours are up, but it has saved its state, and the next job picks up from there. You don't want to write that to the actual parallel file system. You just want to have a place where it's stored, and you quickly read it in again. Burst buffer. Maybe you have some genomic data that you want to compare with a reference database, and you're referencing that database all the time. Maybe you put a database on the burst buffer, and then you read it from there so that your many I/O is bad. Or maybe you have a program that you didn't write, but it produces 1 million files, and our file system says, no, you're not allowed. Put it on the burst buffer, it produces the 1 million of files, and then after the job is done, you just remove them because you didn't care about those files. They're just intermediate files. So there's all kind of cases that we can think of where we would probably before would have said, put it on the RAM disk, but the RAM disk is per node, it's not shared. This is kind of a RAM disk equivalent that can work across nodes. So it's going to be very nice, but we haven't quite gotten to configuring it yet. So that's the end of my diatribe. More information, there's a number of sites that I can point you at. We have our own main site, but that has mainly stories. There's a Niagara page on the Compute Canada wiki, which is called docs.computecanada.ca/wiki/Niagara, which also has user start. There's also a docs.signup.utoronto.ca, has similar information. We're still sorting these things out ourselves, what goes where. What is nice, I will say, about the Compute Canada one is that the information there will be supported in both languages, the French and English. We would like to be able to do that everywhere, but we're only so many people, so we really like leveraging that aspect here. The system status for now is here. There's a link on where the system status is on most of the other sites as well. This will eventually migrate to something better. This is a red dot or a green dot that I drew with a very bad application. So this is me. But if the status is a system is down, that's where it should go. Training, I will give you this, but there's training all out Compute Canada, but this is our training. Most training is local. Lots of it is recorded or broadcast, like today's session, so you can check that out. Questions, support, again, because we're in this transition period, you can either write to support@signet.utoronto.ca or Niagara@computecanada.ca. In both cases, the whole Signet team gets these messages, and so we will reply to you, whichever you're more comfortable with. That's fine.